Hello everyone, welcome back to our vector analysis problems. So in this case, we'll be solving this question that we have. So before I begin, don't forget to hit that like button and subscribe. Alright, let's get to it. So I'm just changing my pen to, let's try black. Alright, so we've been told to calculate the x component and the y component of the vector with magnitude 24 and direction 56 degrees. Okay, so in this case, we haven't been given all the information that we need. We haven't been told exactly where this vector is. So we're going to pick an arbitrary view. So let's assume we have the y and the x-axis like that. So let's assume the vector as the magnitude of 24.0 meters, and its direction is from the positive x-axis. So this is 56.0 degrees. Now to resolve this, we just have to move in the positive x and then in the positive y. So as you move in the x, you have the x component. So the x component will be the magnitude 24 times cos 56. And if you compute this, well, you say 24 times cos 56, you get a value of 13.42062968. If you round this off to 2 decimal places, then the x component will therefore simply just be 13.42. Since the resultant, which is just the magnitude of the initial vector we have, in this case to be precise, is in meters, then even the components will be in meters. So let's be mindful about that. So that is our component value. Then for our y component, to simply be the same procedure, but remember that where the angle points is where you have your sign. So about that, y component will be equal to 24 sine 56.0. So the y component will then be 24 times sine 56.0, which will simply be 19.89690174. Therefore the y component, if I round off to 2 decimal places, will be 19.90 meters. So basically these are the components we needed to find. Alright, so in this question, basically we've been asked to say that a vector A has the following components. It has the x component to be minus 5 meters and the y component to be 9 meters. We've been asked to find the magnitude of this particular vector. Alright, so basically all we're supposed to do is to use the formula. Magnitude of vector A is equal to the root of ax squared plus ay squared. This is the same as the root of ax is minus 5 squared plus 9 squared. And if you want, you can just compute everything in advance, say 5 squared plus 9 squared, get that answer, which is going to be 106, and just root it. And you basically get 10.295630114. Therefore, rounding this off, we get the magnitude of 10.30 meters. Now, the second one asks for the direction. So this was A. For the direction, remember, theta is equal to tan inverse of ay over ax. It's always the y component over the x component. Tan inverse of ay is 9 divided by ax, which is 5. And this would basically give you, if you say tan inverse of 9 divided by 5, you will simply get 60.94539959. Rounding this off, you get 60.94 degrees. But this won't be the final answer, because if you check your quadrant, you find that the AX is negative or the AY is positive. So it's going in the negative, then the positive, which means it's in the second quadrant. So therefore, the direction theta, I'll call this theta prime, is simply equal to 180 minus theta what? Prime. So theta is equal to 180 minus 60.94. So should be 95, sorry, if you round off, 95, because this number is actually equal to 5. 95. So you have 180 minus 60.95, and you basically get theta to be equal to 119.05 degrees, and this is the direction. So you can say that vector A has the magnitude of 10.30 meters at an angle of 119.05 degrees. Alright, so for this question it says a commuter airplane starts from an airport and takes a route shown in the figure. The plane first flies to city A, located 175. So we can collect some data so we can have some information. So we're saying that the plane first flies to city A, located at 175 kilometers away in a direction of 30 north of east. Okay, so we know that the vector A has magnitude, so I'll just say magnitude of A is 175 kilometers. And we know that it's in the direction that is 30 degrees north of east. Then next it flies for 150 kilometers. Okay, so we have next it flies, okay, so it's going to be vector B. So for vector B, it flies 150 kilometers at an angle of 20 degrees west of north. Then that is to city B. Now finally the plane flies 190 kilometers due east to city C. Okay, so that is for vector C. Okay, so from B to C, that is that. So O to A is this, so I can call this O and say O to A. Then this was A to B, and this was B to C. Okay, so let's just put that in mind. So they're saying that it flies 190, so the magnitude is 190 kilometers, and it's due west, just due west. So this is just west. Now saying find the location of city C relative to the location of the starting point. Okay, so we want to find the size of this vector right here. Now, for you to know the location of city C from the initial point going there, in simple terms, you're looking for the resultant. Because to move from O going to C, you're supposed to go from O to A, then from A to B, then from B, you finally go to what? C. And you will have O to C. So in short, you're looking for the resultant what? Vector. So the easiest way we can solve this is by using the Cartesian method. So we're going to resolve these forces we have into their x and y components. So let's begin. So I'll start with vector A. So vector A is here. So I'll go in the positive x and the positive what? Y. So I will move in the positive of the magnitude of A. The magnitude of A is 175. So I'll say 175 cos theta, which is 30 degrees, like that. So basically that's in the I, and to be plus 175 sine 30 in the J. Then you can basically just compute these values that we have to get just one perfect value. So if you do up 175 times cos 30, you will get yourself one. I'll run by rounding off my values to two decimal places, so you're getting properly 151.55. That's in the I. Then if you do 175 times sine 30, you basically get 87.5. So it's a plus 87.5. That's in the J. So you have your components for A. Then find the components for B. So for B vector, I don't even know why I'm putting the magnitude sign. Okay, let's not be putting the magnitude sign. We're just caught up in the magnitude world. Yeah, it's a vector joke. Alright, so let's move on. So for B, sorry, it's supposed to be for B. I don't know what's going on. I don't know. Okay, let's continue. So for B, I resolve B. B is 150 and an angle of 20. So we're going in the positive J, then negative X, like that. So in the positive J, so that's 150 cos 20 in the J minus 150 sine 20 in the I. So punch in this. If you punch 150 times cos 20, you get 140.9538, but I'm rounding off like I said. So we'll have 140.95, that's in the J. Then you have 150 times sine 20, which is going to be minus 51.30 in the I. Therefore, B vector has the components minus 51.30 in the I, then plus 140.95 in the J. So we have those components for B. Then finding the components for C. Now C is only acting, C is like moving from B going toward C. Now this is only acting in the negative X. So you only have the X component, which is going to be minus 190, sorry, in the I. Then 0 in the J. So all we're supposed to do now is to sum up these components. So find the sum of the F. These are the forces? No, the kilometers. So find the sum of the I components. And this will be 1151.151.55 plus, should be a minus because for B is minus 51.30, then minus 190. And the summation of the I components will be, if you say 151.55 minus 51.30, then minus 190, you will get your value to be minus 89.75 kilometers. That's for the I. And you sum up the components for the J. You get that first value, which is 87.5. Then you get 140.95. Then you have 0. So the sum of the J components is equal to, if you do your 87.5 plus 140.95, this will basically give you 228.45 kilometers. Now let's just find the magnitude. So I'm going to erase this portion here so that we can find the magnitude. So the magnitude of the vector we're looking for, which is a resultant, is going to be equal to the root of our sums, sum of the I component squared plus the sum of the J component squared. So r, which is the resultant, is equal to the root of I component, you get minus 89.75 squared plus the j component, you get 228.45 squared. So r is equal to, if you compute that, you know you have your 22845 there squared, you get that with the last to the first, plus you do your 89.75 squared as well. Then find the root value of that, you get to have 245.4474791. So I erase this guy. 2 decimal places, the resultant is basically 245.45 kilometers. You can also find the direction, which is theta, being equal to tan inverse of the j over the I. So the j component is 228.45 over the I, which is 89.715. So I erase this. So theta is equal to the tan inverse. So when you do 228.45 divided by 89.75, then you do your shift tan inverse, you get 68.55 degrees. Now basically I'll call this prime because I haven't really concluded on the quadrant that we're playing in. So if you look at what you have, it's a negative and that's the positive. So it implies that what we're having is this. We're having a scenario where it's like that. So you're having in the negative x, then the positive y. So it's in the second quadrant. So theta is equal to 180 minus theta prime, which is 180 minus 68.55. Therefore, theta is equal to 180 minus 68.55, and that will basically be 111.45 degrees, and that is your direction. Alright, so for this problem it says a force F1 of magnitude 6 acts on an object at the origin in a direction theta, which is 30 degrees above the positive x-axis, as you can see in this figure. Alright, so it says second force F2 of magnitude 5 acts on the object in the direction of the positive y. Find the magnitude and the direction. Alright, so basically let's start with force 1. So force 1, we know it's 6 newtons. So force 1 is acting at an angle of what? 30 degrees. So it's at that angle, that small angle there. So we know we'll be going in this direction, then that direction. So let's find the components. Okay, so the force 1's components will be 6 cos 30, that's in the I, then plus 6 sine 30 in the j. Then all we have to do is to compute this. So you get your calculators, do 6 times cos 30, you get 5. So I'll be rounding off to 2 decimal places. So you have 5.20 in the I because it's 5.196. So that would basically be like 5.20. Then you do 6 times sine 30 and you get 3. So this will be plus 3 in the j. So these are the components for F1. Then we find the components for F2. A second force F2 of magnitude 5 acts on an object in. So this is only acting in the positive y. So we're only having the j component. So for F1, or F2, sorry, we're only having the j component, which is 5. So we're having 5 in the positive j, but 0 in the I. So since the magnitude we're looking for, we have to find the sum of the I components. And in the I components, we have 5.20 plus 0, which will be just 5.20 in the I. Then the sum of the j components will be you get the j component there, which is 3, plus the other j component there, which is 5. So this would be 3 plus 5. So 3 plus 5, that's 8 in the j. So we can find the magnitude. So we know magnitude of f. So f resultant is equal to the root of sum of the I squared plus sum of the j squared. So the magnitude of the resultant will be, you have 5.20 squared plus 8 squared. So the magnitude will be equivalent to, so if you do your 8 squared plus 5.20 squared, then you root that, you get 9.54148, something like that. Rounding off decimal places, you get 5, 4. The components of F1 and F2 are having newtons, so it's also being newtons. Then you find the direction. Theta is equal to tan inverse of sum of the j over sum of the I, like that. So theta is equal to tan inverse of the j is 8 over 5.20. Theta, right there. So if you do 8 divided by 5.20, then do shift tan answer, you will get 56.9761324. Therefore, theta is equal to 56.98 degrees. Now, these components are positive here and there, so no need of checking the quadrant. It's in the first quadrant. All right, so this can just be written as FR is equal to 9.54 newtons at an angle of 56.98 degrees. And that's how you solve it. So make sure you understand.